Hello everyone and welcome to the first lesson for Chapter 5 of the Foundations of Scalable Systems. At the heart of any system lies the unique business logic that implements the application requirements. In distributed systems, this is exposed to clients through APIs and executed within a runtime environment designed to efficiently support concurrent remote requests. In this lesson, I'm going to focus on the pertinent issues for achieving scalability for services, starting with application programming interface design. In the simplest case, an application comprises one internet-facing service that persists data to a local data store, as shown on the slide here. Clients interact with the service through its published API, which is accessible across the internet. An API defines a contract between the client and the server. The API specifies the types of requests that are possible, the data that is needed to accompany the requests, and the results that are obtained by calling the methods. APIs have many different variations, as I explained in the RPC RMI lesson. While there remains some API diversity in modern applications, the predominant style relies on the HTTP APIs. These are typically, although not particularly accurately, classified as RESTful. Very briefly, REST is an architectural style defined by Roy Fielding in his PhD thesis that defines a very specific API design approach. A great source for REST API knowledge is the REST in Practice book by O'Reilly. In this lesson, I'll only describe the HTTP Crud API pattern. Basically, Crud stands for Create, Read, Update and Delete. The pattern does not fully implement the principles of REST, but is widely adopted in internet systems today. It exploits the four main HTTP verbs, namely post, get, put and delete. A Crud API specifies how clients perform operations in a specific business context. For example, a user might want to create a profile using the post HTTP verb. They might read catalog items using get, update their shopping cart using put, and delete items from their order using delete. An example HTTP Crud API for the example ski resort system that I described in earlier lessons uses the four core HTTP verbs is shown on the slide here. In the example, parameters passed are part of the request address and identified in curly braces. Additional parameter values can be passed and returned in HTTP request and response bodies, respectively. For example, a successful request to a HTTP GET example here will return a HTTP 200 response code and the results formatted in JSON, as you can see here with the username, email, and city. To change the skier's city, the client could then issue a PUT request to the same URI with the request body representing the updated skier profile. In this case, the city is changed to Wenatchee. More formally, an HTTP Crud API applies HTTP verbs on resources identified by URIs. In this example, a URI that defines skier 768934 is shown on the slide. The combination of HTTP verb and URI define the semantics of the API operation. Resources represented by URIs are conceptually like objects in an OO system or entities in an entity relationship model. Resource identification and modeling hence follow similar methods to OOD and ER modeling. The focus, however, is on resources that need to be exposed to clients in the API. HTTP APIs can be specified using a notation called OpenAPI. The latest version is 3.0 and a tool called SwaggerHub is the de facto standard to specify APIs in OpenAPI. The specification is designed in YAML, yet another markup language, and an example is shown on the slide here. It defines the GET operation on the URI/resorts. If the operation is successful, a 200 response code is returned along with a list of resorts in a format defined by a JSON schema that appears later in the specification. If for some reason the list of resorts operated by skico.com returns no entries, a 404 response code is returned along with an error message that is also defined by a JSON schema that's not shown here on the slide. API design is a complex topic in itself, and delving deeply into the area is beyond the scope of these lessons. From a scalability perspective, though, there are some issues that you should really bear in mind when deploying APIs. Each API request requires a round trip to the service, which incurs network latency. A common anti-pattern is known as a chatty API, in which multiple API requests are used to perform one logical operation. This commonly occurs when an API is designed following pure object-oriented design approaches. Imagine exposing getters and setters for individual resource properties as HTTP APIs. This simply isn't scalable. Use get to retrieve the whole resource and put to send back an updated resource. You should also use compression for HTTP APIs that pass large payloads. All modern web servers and browsers support compressed content using HTTP headers. Compression can reduce network bandwidth and latencies by 50% or more. The trade-off is the cost of the compute cycles to compress and decompress the content. This, however, is typically small compared to the savings in network transit times. So that's a very brief overview of some of the pertinent issues that we have to consider when designing HTTP APIs. Next, I'm going to delve into how we actually implement those APIs using scalable system services. Thanks for watching.